Okay, divide this by 1.8. So we will have 4.915 power 3 divided by 2.4 is equal to 2.048 times 10 to the power 3 minus 15.736 power 3 times 1.5 divided by 1.8. 13.113 times 10 to the power 3. Okay, so let me do it again. 4.915 power 3 divided by 2.4, which is the cross-sectional area. 2.048, 15.736 power 3 times by y distance is 1.5. Divide by second moment of area, 13.113. So 2.048 minus 13.113 is equal to minus 11.065 times 10 to the power 3 psi. Okay. So now we look at B. Okay, stress X at B. So now this will be equal to class again. Okay, 4.915 times 10 to the power 3 divide by 2.4. Okay, let me shrink down so you can see better. Divide by 2.4. Now the bending does not matter because it's at the centroid. So we multiply it by what? By 0. So this will be equal to 2.048 times 10 to the power 3 plus minus by 0. So this is equal to 2.048 times 10 to the power 3 psi. You can see that, right? And then point C, right? Stress X at point C, right? So now this will be equal to positive again, 4.915 times 10 to the power 3 divided by 2.4. And then we know that this is going to be tensile, so it will be plus 15.736. Okay, 15.736 times 10 to the power 3. And then we're going to multiply by 1.5. And then we're going to divide by 1.8. Okay. So this will be equal to 2.048 times 10 to the power 3 plus by 13.113 times 10 to the power 3. Okay. So 2.048 plus by 13.113. So it's equal to 15.161 times 10 to the power 3 psi. Okay. So let me do it. 2.048 power 3 plus by 13.113 power 3. Yep, 2.048 power 3 plus by 13.113 power 3. Well, 15.161 times 10. Okay. So you can see that the answer is the not the answer is the same, but you can see that the normal stress X at point C, right? The tensile stress or the positive tensile stress is higher than the compressive stress. Okay. Now I'm still trying to see, can we do this based on method number 2? I think we can. Okay, so it's where I stop the element. Okay, where I stop the analysis. So I'm going to try dealing this with method number 2. Okay, bear with me. Okay, so I'm going to take this. Yeah, I think it's possible. Let bear with me. Okay, I'm going to use method number 2, and I'll tell you what is method number 2. Maybe I don't stop at point B. Okay, so method number 2, what I'm going to do based on method number 2, or what is method number 2, is to apply static analysis. Okay, i.e., what do I mean by static analysis? Means we are going to have summation of forces in the x is equal to 0, summation of forces in the y is equal to 0, summation of forces in the z is equal to 0. Okay, so how do we do that? No doubt we don't have the distance down here. I'm going to stop the analysis down here. Okay, we're going to stop the analysis here. I'm going to sketch this out. Okay, same thing. But now, this is my element A, this is my element B, and this is my element C. So we know that over here, this is our 4.915. Okay, and over here, this is our 3.441 times 10 to the power 3 pounds. And it's very obvious that over here, I'm going to call this our what? Let's not call it A or B. I'm going to call it at this point, okay, I'm going to call this point capital C. So this is our CX, right? Why is it going towards the left? It's because it has to counter the 4.9115. And then the other one, this will be our CY. Okay. And then we are going to assume over here, this is our moment in the Z direction at point C. Capital C, not small c. Okay, C is a bad thing because you might get confused. I'm going to call it D then. Okay, there's no, the E, F, there's D down here, E, F, G. Okay, we're going to call this G. Okay, so we have GX, we have GY, and we have moment of ZG. We assume it to be in this direction because we're going to assume positive bending moment. Okay. Okay. So now when we use static analysis, right? Watch this. So we say summation about forces in the x direction is equal to 0, right? So when that's the case, you have minus gx plus by 4.915 times 10 to the power 3 is equal to 0. So gx is equal to 4.915 times 10 to the power 3 pounds. All right. And when it's pulling away, it's going to induce a what? Tensor. Right? Because on the left-hand side is pulling away, it's going to induce a tensor. Then the next thing, we don't look at GY first because okay, we have not done shear stress yet, but I'll do the calculation for you. Okay, so we have summation about forces in the Y direction, and this will be equal to 3.441 times 10 to the power 3 minus by GY, the whole thing is equal to 0. GY is equal to positive 3.441 times 10 to the power 3. Okay. Then the last one is we are going to take summation about moment in the Z direction. The moment is going to take at point G. The whole thing is equal to 0. So i.e., we're going to take moment at where my dot is. Okay. So when that's the case, we have minus mzg, right? And then this one is going to induce a positive, right? It's going to induce positive, so it's going in a wait. This is wait. This is going to induce a clockwise, so minus 4.915 times 10 to the power 3 multiplied by a perpendicular distance of 8. And the 3.441 is going to generate anti-clockwise plus, okay, 3.441 times 10 to the power 3 and multiply by 16. Okay, let me write clearer. I'm like scribbling, which I don't like. I do apologize. Okay, so 4.915 times 10 to the power 3 multiplied by 8, and then plus 3.441 times 10 to the power 3 multiplied by 16. The whole thing will be equal to 0. So finally, mz at point G will be equal to what? Will be equal to minus 4.915 power 3 times 8 plus 3.441 power 3 times 16 is equal to positive 15.736. Yeah, 15.736 times 10 to the power 3 pound inch, and the direction is going this way is correct. So IE over here is compression again. Down here is tensile. The answer is the same. Either you use method number 2 or when using method number 1. Okay, or using method number 1. As you can see from here, we are using method number 1. Okay, now the difference is this. Method number 1, we did not do what? I mentioned about what? Forces. We did not do static analysis. We just see how the structure will react. Okay, that's it. Okay, over here, like what you can see over here, we say that the moment, okay, this is minus 3.320. Anti-clockwise is also positive. This is 55056. Then we write moment about z is equal to this. We did not do static analysis using this method that I've just shown you. Either method you use, whatever you are more comfortable, the answer will still be the same. Okay? Anyone, any questions so far? We okay? Okay. I don't hear anything. Now, what if now, okay, I want to go. I want to challenge you. What if now, okay, I'm going to take the same whole thing. Okay. What if now, right, I want to find out what is going on in DEF, right? What's going to happen in there? Something changed. Yes or no? Okay. So now, if you look at over here, what you will see is nothing will change. So AX, right? So now consider element D, E, and F. Okay, right? So now we're going to focus A, D, and F, D, E, and F. So I'm going to use static analysis. Okay, so we know that we have a load down here, right? This is your D, E, F, F. So G. So we call this this region is our point H. Okay, this is bad writing. This entire region is our region H. Okay, so we know we have our HX, right? We're just going to induce a tensile. So now we do positive is to the right. Summation about forces in the x direction is equal to 0. So we know that AX 4.915 times 10 to the power 3 and minus HX is equal to 0. So you realize that the external load did not change. Okay, so it's equal to 4.915. Okay, now next we are going to take the moment. Okay, so the moment now, I'm going to have moment H down here. So again, this is based on positive shear assumption. Okay, so when that's the case, I want you to watch this. Okay, so we know that summation of moment Z at point H is equal to 0. So you have minus mh. I want to blow this up and show you what we have. So this one is minus mg. We have minus mh. Yes. Okay. The ax, the 4.915, is going to generate a clockwise direction. So minus, right, 4.915 times 10 to the power 3, and is to the what? Because ax is parallel to the centroid, that's why you take this perpendicular distance. So what I want you all to see is this value and this value still the same. Okay. The difference is when you have ay, now this force is perpendicular to the centroid of interest. So let me sketch the centroid again. Okay. So this is the centroid of interest. So now the perpendicular distance is to the what? Is to the element.